we'll just do a class like this today. Not a big deal. Today we are going to talk about matrices. I showed you one of the sections, kind of gave you a little preview of what a matrix looks like. You had a preview question as well, which nearly everyone solved, but most people didn't actually know how to turn it into a matrix, what the final matrix of that thing would look like. So we'll look at that for a few different examples today and explain what a matrix is. Just the short version is it's the exact same as doing things with a regular system of equations and elimination. It just looks different. Later, we will do other stuff with matrices, which will go to other places, and then that will actually be somewhat different. But for what we're going to talk about today with matrices, it's just a regular system of equations. So we did the substitution and elimination methods last week with smaller systems, 2 by 2, and then a bit larger, 3 by 3 systems. We looked at an application of that. Excuse me. We also talked about break-even points and how those are a solution to a system of equations. So today we'll convert between matrices and systems of equations. Very straightforward. We'll look at row operations, also not too tricky. And then we will actually do some one big proper elimination question using matrices. So last time, if you remember, we had this thing that the student selling the laptops and the phones, and we had this sort of balance trade-off. If she does one of more, then that means, or more of one, it means less of the other. So where's the best balance to earn the most money? This currently is a pretty simple version of that kind of problem, but we'll have a more complex one with more parts going on and trying to optimize and find the best possible solution here. So we'll get to that next week when we do a thing called linear programming. So we will come back to that. We're just kind of taking a side little step here to talk some more about elimination and other ways to think about it. So we did this last time, right? We had elimination. This is one of the systems we looked at last time. Is it? No, sorry, this is the system we're going to look at today. So elimination, there are some operations that we can do. Do you remember what those operations are?
Multiplication and division.
Okay, so multiply, so give me a little more detail with that. What are we multiplying and dividing, and by what?
It's one of the equations, equation 1, 2, or 3, to eliminate one of the variables.
Okay, so that's the goal, is to eliminate, but what's the very basic operation? We can multiply an equation by what?
By a number, for example, 2.
Okay, so by a constant. So by
Yes.
any constant that we might want. So multiply any equation by a constant by 2, or divide by 5, or whatever. And what's the other big operation that we have?
Addition and subtraction.
Addition and subtraction. So give me a little more detail there as well, please.
So we select 2 equations, for example, equation 1 and 2, and then we add or subtract them, which depends on which variable we want to eliminate.
Okay, so that's the goal based on like which thing we want to eliminate, but just the basic operation is take one equation and add or subtract it to another equation. And then, of course, what we were doing most of the time was those two things together. we were multiplying something by a constant and then adding it to some other equation. Okay, and I'm going to say that there's another operation that we can do where we take a row and we just change the labels on them. Let's say if I said, well, I don't want to call that one. I want to call this one equation 3, and I want to call this one equation 1. Is that a problem, or is that okay?
It's okay.
No,
That's
it's
okay. And if I wanted to even switch the positions, so now this one at the bottom, I'm going to write at the top, and the one at the top is going to go in the bottom. That's fine. We don't care what order they appear in. So switching labels on rows is another thing that we can do, or switching the locations of the rows. You'll see why I'm mentioning that when we get to our matrix stuff. Okay, so those are the now 3 kind of big things that we can do to manipulate a system of equations. Maybe we want to move the rows around because it looks nicer to have some particular thing at the top or whatever. All right, so matrices. All of you guys are going to watch this exact same lecture. 2 of the classes are watching a recording of this, and 1 of you is watching this live. So 1 of you saw this already. I'm just going to repeat it for the sake of everyone here. So matrix is this thing on the right. We can see if we look at this system of equations that we have on the left, and this is a big one here, a 4x4 system, then hopefully we can see the connection here. So the system is maybe a little kind of messy. Things don't line up. Here's the Z's kind of looking a little like this here. Maybe we don't like that so much. So we can just take those coefficients, 2, 1, 1, 3, and here we go, 2, 1, 1, 3. And for all the variables here, do the same thing. And then we have a column that represents the W's, a column that represents the X's, and then the Y's, and then the Z's here. And then on the right side of the equation, on the other side of the equal, we have these constants, and we can see those constants here. And this little thing here, this line, we don't need to write this. This is an optional thing, but in textbooks or places where they're teaching you matrices for the first time, they'll put this line in just to help you remember, oh yeah, there's an equal sign there. That means that's where the equals sign goes on each of these. But anything beyond like beginner level material, they won't show that because they expect you to know, okay, we have a 4x4 system, so the final column must be the constants on the other side. So that's what that line is representing, but you won't always see that. And our fancy label for the constants we write as RHS for just right-hand side. It's very creative name, just the right-hand side of the equation, whatever's on the right side of the equal sign. So hopefully this is pretty, like we can see the connection here. Okay, here's the column with the W's, here's the X's, here's the Y's, here's the Z's, here's the constants. And then each of the equations that we had, equation 1, 2, 3, 4, now they're just represented in columns in the matrix. So this easiest application, most straightforward application of matrices is we took the numbers from the system and then we just wrote them into a box. That's it. That's really all that's happening. Just visually representing it differently. Everything's nice and lined up. We remember which variables are each of these coefficients are attached to by just looking whatever it lines up with in the column. And that's it. We just kind of save some time by not having to rewrite the variable names every time. This looks a little cleaner, especially if we have a really big system of equations. So that's the idea of a matrix in the math world. So let's try here. I'll do the, well, we'll just kind of talk through these here. Normally I would give you some time to work and then we'd look at it, but we don't have so much time today because we had the holiday, so we have to try to compress 2 lectures down into one here. So let's look at the one on the left first. If we want to convert this to a matrix. So matrix is going to be some box like this. What is the first row of the matrix?
3,
Yeah.
8,
Mm-hmm.
-3.
All right, 3, 8, -3. What's the next row of the matrix here?
2,
Mm-hmm.
-5.
No, 5.
5,
Why +5?
because it comes to the left side, the
Right.
y.
So remember the matrix, everything's got to be lined up. I'll just give myself a bit more space here. What we are doing in our heads, we are taking equation 2 and we are rewriting it so the variables line up. So 2x, and then we want the 5y on the same side. So +5y is equal to -3. So we're doing this, then we can see exactly how that appears in the matrix. And then -3. If we want, we can draw that little vertical line in here to remind us where the equal sign is, but it's not necessary. Again, if we have 2 rows, that means that we have 2 variables, and then the third row, the third column afterward will be the other side of the equal sign. We can just kind of know that. All right, the next one here. So we have 3 rows, and how large will our matrix be? How many rows, how many columns?
3 to 3.
4 columns, 3 rows.
Okay, so 3 rows and 4 columns. So 1, 2, 3, 1, 2, 3, 4. Actually, let's write the labels on here. So this is our row 1, this is our row 2, this is our row 3, and this is the X, Y, Z, and right-hand side columns. Okay, what's the first row?
2 -5, 3, 8.
And 8. All right, and then the next row, we can kind of see what's happening here. We're just reading off each of the values. 3, -1, 4, and 7, and then the final one, 1, 3, 2, -3. We just read off the constant, the coefficients, and the constants. Okay. So one little point here about when you write your matrices, you can see I wrote both of these with kind of a squared off bracket thing. So like this. It is also fine if you write your matrices with a curved kind of parentheses like this. This is the type that our textbook uses. Both are fine, but what you should not do is write just straight lines like this. That means something else. That's a determinant. It's a different thing we do with matrices that has a different math meaning and value and everything. So if you're going to use the straight lines, you need these little ticks, little hooks to make it like a bracket symbol at the top and the bottom. Or if you want to be lazy and just do quick symbols, curved is also fine, but not only straight lines, just a little, not a style point. Straight lines has a very different math meaning, so don't do that. You're going to confuse people. Okay, so system of equations to a matrix. Let's do this in the other order. Make sure we're comfortable with both. System of equations. So let's do the one on the left here first. How many equations do we have?
3.
3. Okay, so we'll have equation 1, equation 2, equation 3. We're going to have system that looks like this. What is our first equation?
X minus y
Mhm.
plus z.
Read the coefficients.
Plus 2z.
2z
Sorry, is
yeah.
equal to 3.
is equal to 3. Good. So just make sure you're reading those off correctly. The second equation, same thing. We'll have 2x plus y minus 2z is equal to 1. And then for x minus 1 plus, sorry, I forgot there. Y, so minus y plus 2z equals 0. Okay, question here. Did I know that these are x and y and z? Why did we choose those particular variables?
Maybe it's just because it's the most common variables.
Yeah, they're just common. It's just convenience. Like this could have easily been the A's and B's and C's, or the, I don't know, the stars and the smiley faces and the, like, it's just symbols, right? We write whatever we want, but X, Y, Z is, those are common ones that we use, especially when we talk about graphing. So we just put the, choose whatever you want. If you're going to choose weird labels, then just maybe kind of put them at the top first so people know what you're representing, but it is arbitrary. Okay. I think we're getting the idea here. For sake of time, again, I'm just gonna skip over the second example. We just read off each line, and then you rewrite that as a system, and you just add in the variables, and that's it. If it's a 1 coefficient, then we don't need to write the 1. We just write the variable. All right. So the next thing is the operations. So there are surprisingly 3 operations that we can do with matrices when we do this elimination, this solving process. On the left, again, reminding you what the ones that we had are for, the ones that we have for just looking at it as a system of equations. So now if we turn it into a matrix and we want to solve, then we will have 3 different row operations, we'll call them. So because again, each row represents an equation, so makes sense. So the first operation is going to be that we can take one row, any row that we want, and we can multiply it by a constant. We could take row 2 here and multiply that whole thing by 3 or by 5 or something. So same as what we do for the system of equations. Next, we can add or subtract any one row from another row. So add row 1 and row 2. If we're trying to eliminate x here and I add these 2 together, then all right, well, we'll eliminate x there. When we did this for a system of equations, if I said I want to add equation 1 and equation 2 together to eliminate the x's, then the result was equation 1, equation 2, add them together. The result was some new equation, and we called it equation 4. With a matrix, what do we do if I take row 1 plus row 2?
The first row stays the same and the second row changes.
Okay, so we replace one of the rows with the new thing. So we would take row 1, add it to row 2, add row 1 to that, and then if row 1 is, we have a nice 1 coefficient there, so we want to get rid of this x here. So our result, we replace row 2 and we make a new row 2 with the result of our operation. So that's the one kind of difference here. We are not forgetting what the original equation was because we kind of rewrite our matrices as we go. So if we want to know what the original equation was, just look back at your previous step and you'll have it there and you can see what it is. But we only really care about the progress part, or as we go, that's the most important part. So one of our target row will be replaced with the result. That's the one kind of difference. We're going to look at full examples of these things soon. And then the last one is that we can swap rows. If I say I want row 2 to be swapped with row 3, then we just switch them. We just switch the locations. Again, we'll talk about why that can be useful in a moment, but we can just switch any 2 rows that we want, and that's fine. So those are the operations. Again, take a look at the left. It's the exact same thing that we do with a system of equations, except we have the numbers in a box and we don't have the variables written out each time. Okay, so let's actually do these row operations for this matrix that I have here, and then we'll go back to the one on the previous slide and actually solve that system. So we're going to do these 3 things here, these 3 operations. We'll do them independently, so they're not kind of in order or sequential. We're going to just do each of them separately, and then we'll actually do them together when we solve this. So A here. A is asking us to swap rows 1 and row 3. So let's just write our labels. This is row 1, this is row 2, this is row 3. So our resulting matrix here. What is our new row 1?
-2,
Keep going.
3, 0, and then -1.
-1 here. Okay, so we should, when we do matrix operations, we should always write what we're doing, just so we remember, we don't confuse ourselves later if we're going back and checking our work. So row 1 is being exchanged with row 3. We'll just kind of write out on the side what we did on that step, what operation we did to get that result. Our row 2 is the same, nothing's happening there. -1, -4, 4. And then our new row 3 was the former row 1. So 5, -2, -2, -2. So that's our result. We just write on the side what we're doing, and then we have our result. We've swapped those 2 rows. All right, let's do the next operation here, which is B. So multiply row 3 by 2. So our matrix, again, I'll write it like this. Multiply row 3 by 2. So already I know row 1 and row 2 are not changing. So we can just write those in. -2, 4, -1, -4, and 4. So no changes to rows 1 and 2. The only thing that's changing is row 3 here. So let's write our operation on the side. So 2 times row 3. I would write it like this. Sort of treat row 3 kind of like it's a variable. Just like we'd write, 2x or something, 2 times row 3. All right, so can someone please tell me what our new row 3 is?
10,
-8.
10.
I haven't heard anyone say the right values yet.
-8.
Negative 4,
-4, okay.
6,
6,
6,
0, -2.
-2.
yes.
Okay, so there we go. We're just multiplying everything that was in row 3 by 2. And we're done. All right, the last one. C, so getting a little more complicated here. All right, we want to multiply row 3 by 2 and then add that to row 2. So, okay, first, if we do operation C here, which row or which rows will change, and then which row or which rows will stay the same?
The first row will stay the same.
Okay, so row 1, that's pretty obvious. We haven't even mentioned that in the operation. So row 1 will be the same, 5, -2, -2, -2. What about the other ones?
The second one, the third one will be replaced by the result.
Someone else want to give us a try?
Well, the third one will actually change, but we'll add it to row 2, right? So at the end, row 3 will stay the same.
Okay, so we're using 3 to change 2, but we're not, in the resulting matrix, row 3 is going to be the same. We're not actually, we don't want to change row 3. We are just adding 3 to a different one. So the row that's changing is row 2. That's the only part that's changing. So we'll write out our operation here. We want row 3 times 2. So 2 times row 3, and we are adding that to row 2. Actually, let's write that the other way. We'll start with the row that is our target, row 2, and we're going to add 1 to it. So we are adding 2 times row 3. And then that new result is replacing whatever was in row 2 before with that. Okay, so we want this thing times 2 added to this thing here. If the numbers are simple and you can do this in your head, then great, do it in your head. And if you're confident you'll get the right thing, that's fine. If not, never hurts to just write things out on the side here. So let's say 4, -1, -4, and 4. That's our row 2, and our 2 times row 3. 2 times row 3, -4, 6, 0, -2. We figured that out on the other step. And then we're just adding these together. So 4 and 4, that's a 0. -1 plus 6, that's a 5. That's a -4, and that is a +2. So there are the values. If you want to just do this to make sure that you're getting your values correct, that's fine. But the thing that we really care about is not the operation, or like, we don't need to write out the process for the operation. That's just up to you. We care about the results here. So this thing on the side tells us what the operation was, so we can go back and check it for ourselves later if we want, but we really just care about getting the result. So we took row 2, we are using row 3 to manipulate it. We are replacing the old row 2 with this new thing. Again, if we want to see the old version, we just go back and look at the earlier version of the matrix here. But what we care about now is this new thing, and where we've eliminated one of these variables. That's usually our goal. Okay, so those are the operations. Swapping rows, pretty straightforward. Multiplying a row by a constant, pretty straightforward. But we can multiply and then add to another row, and then the row we're adding to or subtracting from, that's the one that's changing. So just make sure you're clear about which row is being replaced and which row is being kept. So here, row 2 is our target, and row 2 is replaced with this new version of row 2. That is, those are all the operations. So we can do quite a bit with this simple set of operations here. We can use this to solve systems of equations. Any questions about this process here before we look at an actual elimination process? All right, let's look at one then. So we'll look at the system that I showed you earlier. And this one is going to be pretty straightforward. We'll get fairly clean answer here. Just in case you want to know, this process here is called Gaussian elimination. I'll clarify the terms in a little bit here, but there are some fancy math terms for all of this stuff. Okay, so what you see on the top is just kind of our guide and what we're going to be trying to do. So when we solve a system of equations, our goal is to get down to this, right? To be fully solved for one of the variables. Doesn't matter which one, but let's say Z here. And then once we've solved for one variable, it's really easy. Just substitute back, we figure out what the other variables are. So we'd make two 2x2 equations, and then we'd reduce one of those, and then we'd get a 1x1, one equation with one variable. Very easy to solve. But if we kind of think of a shape here, we get this sort of pattern. When we do this with our matrix, we're going to do the same kind of thing. That's sort of our goal. We want this triangle shape. Going from this box here to this triangle shape. And with the triangle shape here in the system of equations, you know, that's a 0, that's a 0, that's a 0. We can understand that that's still there. So let's actually try to do this. If we did this with a system of equations, we'll kind of do this simultaneously with the system and the matrix at the same time here. So row 1, row 2, row 3. With a system of equations, what would be your first step using elimination?
You can start 1 and 2 or 1 and 3.
Okay, so adding row 1, equation 1 to equation 2 looks like it would be a pretty useful thing to do, and we would eliminate the x's very cleanly there. So if we take equation 1, equation 2, we don't need to multiply by anything, and we just add them together, and then we will eliminate the x's. So let's do that. X minus 2y plus 3z equals 9, and negative x plus 3z minus z equals negative 6. All right, and we are adding, so the x's are disappearing, so that's 0 here. Our result will have y, and 3 minus 1 plus 2z. 9 minus 6 is 3. Okay, so we've made that, and we will, let's do the next elimination thing with our system, and then we'll kind of mirror that with our matrix. So it's equation 1 and equation 2. I think we can use equation, as we just heard, equation 1 and equation 3 to eliminate the x's there as well. So what will our operation be with equation 1 and equation 3? Are we multiplying? Are we adding or subtracting?
Multiplying the first equation by 2.
Okay, so 2 times equation 1, and adding or subtracting?
Subtracting.
All right, subtracting. I'll try to be consistent with my labeling here. All right, and we are subtracting. So 2 times equation 1 is 2x minus 4y plus 6z equals 18. And equation 3, 2x minus 5y plus 5z equals 17. We subtract, and x's are disappearing again. And here are y's. All right, you guys tell me, what is our result here?
9y.
Y.
So positive 1y minus negative 5 here. So that's so,
Yes.
yeah. What's
Plus
the,
Z
okay, and then
equals
1
1.
equals 1. All right, very, very nice, very clean, very simple result here. So again, let's add some labels to these. We could call this equation 4, equation 5, as we've done in the past. And okay, so let's just take a little pause there, and we'll switch over to our matrix and see how that would work over here. All right, so our new matrix, just write like this. We have our equation, or sorry, our rows 1, 2, and 3. So let's write out our operation. What is the first operation we're going to do?
We're going to add the first row to the second row to
Okay.
get a 0 in the beginning of the second row.
And which row will be replaced by the result?
The second one.
Second row. Okay, so second row is being replaced. So we're going to write our little operation here, or what we're doing for beside the second row. So row 1, -2, 3, and 9, and row 3
Stays the same.
are not going to change, and we are only changing row 2. So again, if you want to write out on the side what the arithmetic is here, just to make sure you're not making any mistakes, that's fine. That's probably good practice for some more complicated ones. But if it's really simple and you think you can do it in your head, then that's totally fine. So 1 plus -1, okay, that's consistent with our colors here. That's a 0, and the next one here, I know we just figured this out on the other side, but always good to double check your work. -2 plus 3, that's a 1. 3 plus -1, that's a 2. And then 9 and -6, that's a 3. Okay, so there is our new row 2. And that's our operation finished there. So we don't have to do, we do some rewriting with the other parts of the matrix, but we'll see in a little bit later how we can actually kind of combine a lot of these steps here. But for now, let's just treat each step separately. What is our next operation here? Again, mirroring what we did on the left there.
We are multiplying the third row, the first row by 2, and then subtracting the row 3 from the row 1.
Okay, let's talk about this in the other order. I'm going to talk about the target row first. So our target row is row 3. We really like having this 1 here in this first position. And I want to turn these other ones into 0s. So row 3 is our target. So I'll just kind of write it in terms of that. So row 3, and we'll subtract from that 2 times row 1, like this. Okay, so the operation you said is right. I'm just going to flip the order around. So again, where our operation is on row 3. So rows 1 and 2 are not changing, so we can write those in. Row 3 is the only thing where we have to do some work. So again, I know we just figured this out on the other side. It's always good to double check what we're doing. But here still doesn't seem too complicated. We can probably do this in our heads. So in this case, so 0, that should work out. -5, maybe it does help. -5 minus 2 times our -2 here. Okay, so that's going to equal -1. That's a -1 there. And then our next one, we have 5 minus 2 times 3. So that's going to be also a -1. And then our last one here, 17 minus 2 times 9, 18. So that's a -1. Okay, so what's different? Why did we get a different result compared to what we did on the left?
You equal the 3 lines in row 1 and row 2 and row 3 as a 1, 1, 1.
Okay, so what we did on the left, we did 1 minus 3, but here we did 3 minus 1. So because we switched the order, these all came out as the same idea, but the signs are all reversed. So what we could do is we could write another version of the matrix just to do.
We could swap row 3 with row 1, right?
We don't want to do that. So let me say what we could do here. So row 3, just take the whole thing and then multiply by -1 and then get 0, 1, 1, 1, and the other parts would be the same. So I don't want to write out, it doesn't seem necessary to rewrite the entire matrix just to flip the signs on one row. So let's be good, lazy math people. And we're just going to take this and say, we're going to do that whole operation and then multiply by -1. And then I will just erase my negative signs and we're done. So let's combine some steps here to make this easier for ourselves. We do not want to we don't want to swap row 1 and row 3. Why would we not want to do? Why would that be a bad idea?
Then the result will be replaced by the row 1, right? That's why we would confuse it. And
do you mean swap as in like reverse the order of the operation here, or do you mean like actually take this whole row and switch it with this whole row?
no, I mean at the beginning, could we do that? I mean, the original row 3 would go to the first order. I mean, will be replaced, and then we could do, and then the labels wouldn't change, right? Would be the same on with the left side.
At the very beginning, like
Yeah.
okay, so from the very beginning, again, what we want, like it's very nice to have ones here, have a 1 in each position, which I'll talk about a bit more in a moment. So we kind of want 1s on this main diagonal here. So if we have a 1 in this first position, we probably want to keep it there. We didn't know that we would get this negative here, but it's not a problem. It's very easy to deal with the negative. We just multiply everything by -1. But I want a 1 here, and then I want these next positions below to be 0. So we have a 1, that's eliminated, it's a 0, that's eliminated, it's a 0. So we've eliminated the x from 2 of all of the other equations. Our result is now this 2x2 system, and a very simple 2x2 system. We can solve this very easily. That's our removing one layer of complexity. Remember, when we talk about the 3x3 systems, we reduce down to a 2x2 system, and then the 2x2 to the 1x1. So,
Mr. Corks, can I ask a question?
Sure.
Why are we subtracting 2 rows 1 from row 3? Why can we do the opposites? Why can we subtract row 3 from 2 row 1s?
Okay, that's fine. This is the same thing, just your signs are going to come out the opposite. I have just written it this way for clarity, it's possible that you could just get a bit mixed up about which where the result should go. So whenever I write this in class, I'm always going to write our target row first. Here's our target row, it was row 2, or here's our target row, it was row 3. And then what are we doing to that target row? We're adding something or subtracting something. So just for consistency, I'm going to write it like that. But again, the signs coming out negative, just flipping the signs is really simple. It's not necessary for us to reverse the order of this. And we don't know necessarily how the signs will come out in advance anyways. Like normally we don't do the system all on the left side at the same time. So flipping the signs isn't a big deal. It's very easy to handle. And we can't necessarily predict that anyways. So it's not a problem here, not really a significant problem. Okay, so we have a 2x2 system and we have a 2x2 system here as well. Equation 4, equation 5, both of them are missing x, which is great. So pretty easy to solve for that one. All right, so let's do that. With the system of equations on the left, what would our next operation be?
We would substitute, right?
We're not. Let's keep with elimination. So equation 4, equation 5. What elimination would we want to do?
Subtract minus row 2 from row 3.
Let's talk about the system of equations on the left, and then we'll talk about how that appears on the matrix.
Sorry.
So we have equation 4 and equation 5. Tell me what we would do here.
We can subtract the 5th equation from the 4th equation.
Okay, so equation 4, and then subtract equation 5.
Because we need to get rid of the y.
Okay, so y's, we have a 1 coefficient on each of the y's. That looks like it's the easiest thing to eliminate. So y plus 2z equals 3. Y plus z equals 1. And we subtract.
And we got z equals 2.
Z equals 2. So everything, this is very, very easy arithmetic here. The y's disappear very cleanly. Z equals 2. And then that's sort of our new equation 6 here. All right. Now let's do the same thing over on the matrix side. So what is our next matrix operation?
We need to subtract the 3rd row from the 2nd to get a 0.
Where will the result go?
The result should go in the 3rd row.
From the 3rd.
Sorry, can we say that one more time? Where will the result go?
To the 3rd.
Like in row 3.
Okay, row 3. So row 3, and as we'll see when we do it, that will give us our triangle shape. As we can see what we did on the left, it's going to give us kind of the flipped signs, but again, we just flip them back. It won't be very hard. So our operation is going to be row 3 minus row 2. Again, just for convention, for consistency, our target row first, and then the thing that we're doing to it written afterward. So row 1 is not changing. 1, -2, 3, 9, and row 2 is not changing. Excuse me. 2, 3, and our 3rd row here. Again, we can write out the arithmetic on the side, but this is not very hard to do. So 1 minus 1, that's a 0. It should be, but we want to just make sure that's going to happen. 1 minus 2, that's a -1, and 1 minus 3, that's a -2. Sorry, I should be doing these in red for consistency here. So -1, -2. And okay, we want positive numbers here. So let's just once more add this extra little operation, multiply the whole thing by -1. And then I get to erase my negative signs. And we have the same result that we had on the left. So we've done kind of the main part here, sort of the hard part. We've done the bulk of the solving work. So on the left, we have a variable eliminated, or two variables eliminated, and then this one solved for, so z equals 2. And then on the right, we've done the same thing. This row means 1 times z is equal to 2. So z equals 2. And we can just very easily take this and substitute back into the previous row, and then take those two and substitute into the previous row. So we can solve very easily for the remaining two variables. What I want to draw your attention to here is the shape. So with our system of equations, if we took our equation 4 and equation 6, and then equation 1 as well at the top, we've kind of made that triangle shape. And then look at what we have in our matrix as well. We have that same triangle shape here, because the zeros have been eliminated and we have ones on our main diagonal. So if we have that, it's very easy to solve the rest of the system here. That's our goal. Ones on your main diagonal and zeros on everything below that main diagonal. So as I put in our guide at the top here, that's the shape. We want the triangle shape. And then whatever the constants end up being on the right, that's going to tell us what everything is equal to. Okay, so system of equations, which we're hopefully familiar with, and then what we're doing with the matrices. The labels are slightly different, and maybe we had to flip the signs over, but it is the same basic process. It's the same thing happening. It just looks a little different. If you are wondering right now, why on earth are we doing matrices if it's the same as the other thing? Well, if we have a huge system, it can be faster to do this, so we don't have to do all that writing. It is nice and clean and organized, just this sort of nice kind of big column of operations here. But the real thing that is nice is, let's say these two steps here, we did something to change row 2 and we did something to change row 3, and both of them involved row 1. So really, those two steps we can combine and write into just one step. So two different operations, but we only have to rewrite our matrix one time instead of having to do all of this rewriting over here. So combining the steps, multiple like independent operations, but we can write them at the same time, saves us a lot of space, makes the work look a lot more clean. Okay, so that's half of it. Let's just do a quick little recap here. So operations on the left, we can multiply by a constant. We can do the same thing with rows of a matrix. We can add or subtract one equation to another equation, add and subtract one row to another row. We just be careful about which row we are replacing. Which one is the one that we don't want anymore? And then the results, which one is the more useful thing? So where is that result going to go? We have to think about that. And then swapping rows, which we didn't need to do in this case, but it's, again, a very simple thing to do and can be useful. All right, let's look at the next kind of part of this, which is where, and there's a fancy name here, Gauss-Jordan elimination, where we can actually go back. We can do the whole thing with elimination and not not using substitution going backward. So I've kind of, cheated here just for sake of time, written out what we will expect to happen. And, if you're looking at this, we can already see, okay, well, if z is 2 and y plus 2z is that, okay, like it's a pretty simple, easy system to solve here. So, but what we're going to do is, instead of doing substitution, we're going to use elimination going back up instead of doing substitution. So this is the thing that is not usually done with a system of equations, but this is the standard way of solving matrices. So again, we'll see what it looks like with the system, and then we'll repeat it with the matrix on the right here. So we have, or let's keep our labels. This one was our 4th equation, and then this one was our 6th equation. So 1, 4, and 6 here. If we had this system with equations 1, 4, and 6, and we want to do elimination to solve for the next thing here. Let's say I want to use rows 4 and 6. I want to eliminate the z to solve for y. How would we write the elimination process here? So I have row 4, I have row 6, and I want to eliminate z.
We would multiply the 6th equation by -2 or 2 itself.
Okay, so let's just say +2, and then are we going to add or subtract?
Subtract.
We will subtract them. Okay, so we'll have y plus 2z equals 3, and our other equation is 0y plus 2z equals 4. And then we will have here our y plus, okay, the z's are going to disappear, 0z, and then 3 minus 4, that's -1. So y is equal to -1. So I know that might feel like kind of a lot of extra work where we could just do this with substitution very easily, but elimination works going back up as well, not just getting down to one variable. We can work our way back up with elimination. Okay, all right. And then if we want to solve for x as well, we might actually need kind of 2 more steps here. So if I want to, I have x in equation 1, how will we try to solve for that? Let's say first we want to eliminate this z. The z in equation 1.
We multiply the 6th equation by 3.
Okay.
And then we subtract again.
So x minus 2y plus 3z equals 9. And equation 6 by 3, 3z equals 6. And we are subtracting. All right, and our results, so x, that's not going to change, minus 2y, that's not going to change, but 3z, 3z, so that's 0. So 9 minus 6 is 3. Okay, so we've made this new equation here. Call this, actually, I guess we could call this one our 7, and this one an equation 8. So let's take a pause here. Let's see what this would look like over with our matrix, and we'll see how we can combine some of these steps here. All right, so those two things, let's say the first one, where we solved for y, what would we do in our matrix to mirror that process? Again, rows 1, row 2, row 3.
Row 3 multiplied by 2.
And
Subtracted row 1 from row 1. I'm sorry.
okay, you're thinking of the second step here. So let's do
I'm sorry. Row 2. I'm sorry.
Okay, so we'll take row 2 and we will subtract from that 2 times row 3. So row 1 is not changing. Actually, let's save that for a moment. Row 3 is definitely not going to change. Row 3 is perfect. It's totally done. We don't want to do anything to row 3. So row 2 minus 2 times row 3. Again, we could write out the arithmetic on the side. This is pretty straightforward. So let's just write in our numbers here. That's a 1. That's a 0, which it should be. Good to double check. The only value where we actually have to do some math here, 3 minus -2, that's going to turn into -1. Okay, so once again, let's be good math people, which means let's be lazy. I don't want to write this matrix more times than necessary. So let's take our second operation that we had over here. Let's do that at the same time right now. Let's combine some things with our matrix. So tell me the second operation that we did with the system on the left. Tell me what that is in rows.
Now we are taking the first row. And we are subtracting the second row multiplied by 3, I guess.
Not the second row.
Third row. I'm sorry, the third row.
Third row. So row 3 times 3. Okay, so we're gonna just do this at the same time. And our results, so with row 3, 1 minus 0, that's a 1. -2 minus 0, that's -2. That's not going to change. We do want to eliminate that, but that'll be the next step. And then here we'll do
0.
This is 0, which it should be. Again, good to double check.
And here we get 3.
And 3. All right, so we've combined 2 steps. Look at this big thing that we wrote on the left versus just this nice little clean thing that we did on the right. So there's kind of an advantage with matrices. We have one more step we want to do. Okay, normally I would do this with the system, but just because we're running out of time a little bit, let's just finish this up with the matrix directly. All right, what is the final thing that we are going to have to do to complete our matrix?
Maybe we need to get back to the system of equation.
We haven't solved for all the variables with the matrix yet. We still have this -2 that we don't want.
We have to
So then
multiply the row 2 by 2 and then add to the row 1.
All right, so row 1
plus 2
add
row
to that, 2 row 2. Okay, so this operation, here we have 1 and 0, so that's going to be a 1. We have 0 and 0, that's going to stay as a 0. -2 plus 2, that position should turn into a 0. So the only actual math we're doing is in this final position here. What's our value there?
-1, I guess. 1, positive 1.
Positive 1, okay. So there is our full solution here. So this row is telling me, like, again, 1x plus 0y plus 0z equals 1. That's the same as just saying, okay, x is equal to, erase the equals, x equals 1. We can just read that result very, very easily directly off the matrix. The next row is telling me y is equal to -1, and the final row is telling me z is equal to 2. So there is our solved system here. So doing a system of equations, doing elimination going backward, it is kind of a little weird. It's like a bunch of extra writing that doesn't seem necessary. But when we do that with a matrix, we combine a lot of steps. The arithmetic is quite simple going back up. It goes quick and it looks nice. It's a much sort of simpler looking result here. So definitely saves us some time and once you're familiar with it, and keeps things organized. It's a lot easier to look at a solution and look at someone's steps or someone's process for a system of equations as a matrix versus just the regular system. Okay, so that's the basic process. I do have more examples and stuff that we'll go through. Those are all going to be in the workshop for this week, which is today. It's going to be later today. So I'll have a bunch more examples of some simpler things with matrices that we did earlier, and then a few more like big full elimination questions like this, but without the mirroring on the left, just looking at things as a matrix. So more practice there. But again, if it's confusing, if it's weird or anything, if it's hard to follow, just remember whatever you would do with a system of equations, you're doing the same thing with the matrix. So we went from this triangle shape here down to this ones on the main diagonal and then everything else as zeros. That's the shape. So let's actually just talk about that one more time here. So our process, if we're starting with the matrix, we're going to have a box. And then we go from the box to having what we want is this triangle shape. That is actually what it's called, the upper triangular form. And basically that means that these are all zeros. The values below the main diagonal have all been turned into zeros. And then from there, our final step is to get this shape. So it means all zeros below and all zeros above our main diagonal. And then we just read off our values. What's X? It's whatever's on the right side. What's Y? Whatever's on the right side. What's Z? Whatever's on the right side. So that's what a kind of a solved or completed or fully reduced matrix looks like. So box to triangle to diagonal, which here's kind of the steps written out. If you want to take a screenshot of this, it's the same thing that I just explained, but in text and graphical form here. Okay, so I have a few things to mention about. Okay. Yeah, I wanted to have some time to talk about this. We're a little low on time. For next week, we're going to start talking about inequalities and graphing inequalities because we need that to do a thing called linear programming. So what I wanted to do was spend some time graphing. All right, let's do one of these and then I will maybe just kind of do a video version of the rest of this. You're gonna kind of need this for the preview question for today. Okay, y is greater than x plus 4. If I want to put that on a graph, how can I do that? How can I graph that?
The slope will be 4 on the y, right?
That's the y-intercept.
All right, the 4 is the y-intercept. So that's our y-intercept right there. What's our slope?
1.
1. So first step is imagine that it's just an equation. So y equals x plus 4. So slope is 1, y-intercept is 4. So that's going to give us this line like this one and both directions. Okay, so that's step number 1. But we have an inequality. So what else do we have to do with this?
Shade some part of the graph.
Okay, so we have to shade in. So the y is greater than x plus 4. So either this whole side is the solution space, or this whole side is the solution space.
Left one.
Why the left one?
Because this line is increasing, so that's why. Upper means left side.
Okay, so this greater than. So we have this line of y equals x plus 4, but we are saying for this y must be greater than this. So y values must be greater, bigger y values means up in our graph here. So we are shading above the line. One other way of testing that is just take any point on the graph. Let's choose a really simple point here, like say 0, 0, and put that into the inequality. So y is greater than x plus 4. Let's substitute in the values of 0 greater than 0 plus 4. So 0 is greater than 4. 0 is greater than 4. Is this a true statement or a false statement?
False one.
This is false. So what does that tell us about this point and our inequality?
The right part, not the.
Yeah, because the numbers that are allocated in the right part, they are lower and they're false to the statement.
Okay, so if the statement is false, we just test any point, throw it into the inequality, test it. If the statement is false, then this means this point is not included. It is not inside the inequality, so it must not be this side. It must be the other side of the line. And this whole space is the space of solutions for this inequality. So check any point, test it, and see what you get as a result. All right, we're not done though. There's one other thing we need to do to finish drawing this. Look at the inequality. It says y is greater than x plus 4. So there's one thing that's currently on our graph that's incorrect.
Oh, dotted lines.
Okay, so dotted line. So the actual line of y equals x plus 4, the line itself is not included. So this is the proper situation. My dotted line is not perfect there, but so it's the space that goes up to this line, but doesn't actually touch it. If we had a situation like we have with the second example, which we don't have time to do, I'll make a little video about this, where it's like less than or equal, greater than or equal, then yes, it does include the line. But if it's just strictly greater or strictly less, then it does not include the line. If it doesn't include the line, a dotted line is how we would represent that. Okay, that's the basic bit. There is actually a bit more I should be saying, but we are out of time, unfortunately. I'll make a little video explaining that, which you may or may not need to help you do the preview question for next week. But I'll do a summary of everything else that we talked about here. So converting a system of equations to a matrix, and then a matrix to a system of equations. Converting is pretty easy. Row operations, just if we're adding or subtracting two rows, be clear about which one is our target. And then solving a system of equations from box to upper triangle to main diagonal only. Just remember those shapes. That's what we're trying to do. Matrices are used a lot, so please take some time to actually, and the homework for this week as well will require you to do this as a matrix, not with a system of equations. So learn both of these methods. So learn the matrix method also. It will help you with a lot of math stuff. Okay. Our review questions, there's a whole bunch of review questions. We'll be doing some of these in the workshop this evening as well. Preview question, again, I'll make a video explaining, not showing these questions, but explaining a bit more of the graphing stuff with this in case you haven't done this before. So the two questions, if we have this inequality, are these 2 points solutions or are they not solutions to the inequality? And then the second one is a little more interesting. Let's say we have a graph with these 4 inequalities together as a system of inequalities, the shaded areas, and then you combine those shaded areas, and then what is the one final resulting shaded area that's true for all 4 of them at the same time. So as a system, if we did that, then it's going to create a shape. If you put them on a graph, you'll see an actual shape. What does that shape look like? Just describe it in words. It's a circle, it's a triangle. Like, what is the shape? And then calculate the area of that shape. Once you see the shape, it will not be hard to calculate the area. But try to do the graphing and see what the system, the result of a system of inequalities looks like. That's the preview question. The homework question, just fine-tuning 1 or 2 things, and then I'll have that posted on our classroom page quite soon. If you are watching this live, so section 3 people, section 1 and 2, because we had the holiday, they are watching a recording of this lecture. So I am not going to post the actual preview question, the actual numbers for it on the classroom page. They have to watch this video to then see what the numbers are to do the preview question. So if your friends in the other sections ask you what are the questions, tell them, nope, you have to watch the video. It'll be posted soon for them. Okay, so please help me out with that. All right, so system of inequalities and then linear programming is our topic for next week, and we'll get there. Okay, all right, we are very over time. Sorry about that. Enjoy the rest of your day and yet another weekend, and then I'll see you on Tuesday next week.
Thank
Goodbye,
you,
everyone.
Professor.
Thank you,
Thank you very much.
Professor.
Bye-bye.
So
Thank you, Professor.